Okay, good morning, guys. It is Mr. Citro here. It is Tuesday. I was trying to get this out yesterday, but I'm having some internet issues, as I know many of us are experiencing. So I just want to touch base, say hello, go over the concept of this week, which is relative humidity and dew point, and how they are related, and how temperature and dew point can help you determine relative humidity. Now, there is a large portion of this unit or this concept in your reference table. But for right now, let's go over these major concepts, and we'll spend the rest of the week looking at the reference table and those questions. So first thing, humidity is a measure of how much water vapor is in the air. That means how much water takes up each individual air molecule. So we have an air molecule, and within that air molecule there is water vapor. How much of that air molecule's space is full of water vapor? You could think of it as a room or a glass. That glass represents an air molecule. How much water fits in that glass? Well, if the glass is full, we would say 100%. So if the humidity is 100%, that means that the air has a relative humidity of 100% and it is full of water vapor. Now, that previous slide mentioned that warmer air can hold more water vapor, and that is because when we heat something up, it expands, if you think of the first unit. So at 10 degrees Celsius, the space that the air molecule takes up happens to be the same amount of space as the water vapor takes up, meaning that it is now 100% full. But if we heat up that air molecule, let's say we heat it all the way up to 30 degrees Celsius, we notice we still have the same amount of water vapor as we did at 10 degrees. But the air molecule takes up a lot more space. So when we compare the water vapor to the air, we notice that there's a lot less water vapor in comparison to the size of the air molecule. So in summary, we look at this slide, we notice the amount of water in every case is the same. But as temperatures go up, we see humidity decrease. And that is because warmer air can hold more water. Now, can air at 30 degrees Celsius have a relative humidity of 100%? Yes. It would just require a lot more water to fill that space. So that's relative humidity, how full the air is with water vapor, and we use it as a percent. And as we mentioned, warm air holds more water, meaning that warm air tends to have a lower relative humidity, or as the air warms up, it has a lower humidity. We've covered saturation before. Remember, saturation means something is full. In this case, we're going to say if air is saturated, it has a maximum amount of water vapor or has 100%. Now, when the humidity is 100%, it's saturated and we have condensation occurring, which means clouds can form, rain. We see condensation sometimes on the outside of a glass that has ice cubes in it, and that is because the water gas is condensing into a liquid. When we see clouds form, that means that there is a 100% relative humidity. Essentially, all of the gas, the water vapor in the air has begun to condense and form clouds. Now, precipitation will take a lot of this water out of the air, meaning that it becomes drier in the air after it rains. And it usually has a little bit of a lag, but most of that water vapor condenses and forms liquid water and then falls and makes its way to a liquid water source such as an ocean, pond, river. Evaporation then occurs once it finds its way back down to the surface, that water, and that puts the water vapor back into the atmosphere. So evaporation causes water vapor to enter the atmosphere. Precipitation causes water vapor to condense and fall back down to the surface. Most evaporation comes from our oceans. We did cover that a few units ago. And here's where it gets a little crazy or a little confusing. So bear with me and just take a minute to look over this. The dew point temperature is the temperature at which the air becomes saturated. So what that means is if the air temperature reaches the same temperature as the dew point, like we see over here on the right, we have a very high humidity. Again, the dew point is the temperature at which dew forms, meaning water vapor condenses to form liquid. So if we reach that dew point, or if the dew point happens to meet with the air temperature, that means, boom, all of the water vapor is going to condense and form a cloud, and precipitation will begin. Now, on the other side of the spectrum, if the air temperature is a lot higher than the dew point temperature, we see a large change here, we would have a low humidity, meaning it's probably dry out. Again, the dew point temperature is the temperature at which dew will form, meaning water vapor will condense. We can never have a dew point temperature greater than the air temperature. They can only be the same, and when they are the same, the humidity is 100%. Here's an example of what your graph is going to look like, and this is going to be one of the major concepts we're hoping to gather from the third week of this project. When we create this graph, we're going to see an air temperature line and a dew point temperature line. And the key is the closer that these two are together, the higher the humidity. Again, the air temperature is very close to the dew point temperature, and the dew point temperature means that water vapor will condense and form dew or clouds, and rain will most likely occur. So at 6 a.m., we would expect to see the largest or the highest amount of humidity right here at 6 a.m. And that is because they are closest. On the other side of the spectrum here, at about 4 p.m. right here, the temperature and the dew point are further away from each other. And that means that we probably will have a low relative humidity. The air will be pretty dry, and we would not expect there to be a large chance of rain. Now, this trend tends to be what we see on a day-to-day basis, and that is because as the sun is out during the day, if we see here 6 a.m., this is about sunrise, and 6 p.m. is about sunset on average. So during the day, we're heating up, and we're warming because of the sun. And when we warm up, the air temperature rises, but we don't expect the dew point to rise. The dew point temperature is not controlled directly from the amount of sunlight we get. Our air temperature is directly related to how long and how much sun we get every day. So during the day, the air temperature rises and gets further from the dew point. Then at night, the sun is gone and we start to see a drop in the temperature. And as we will talk about, the coldest portion of the day is around 6 a.m. So we tend to see the highest humidity in the morning and the lowest humidity around 2 to 4 p.m. And that is an average day-to-day basis. We measure it using a sling psychrometer. We have a lab on that, but we will not have time to complete that lab. But the wet bulb and the dry bulb determine the difference from evaporation, which is the wet bulb. Essentially, we put a little bit of water on this wet bulb, which is a thermometer that just has a small piece of cloth on it. And the dry bulb does not have a piece of cloth on it. And we swing this around for about 30 seconds, and we read the difference between the two. Now, first thing we notice is that the wet bulb is 15 degrees, and the dry bulb, let's say, is about 21 degrees Celsius. So they're not the same. We could tell right now that because they're not the same, we do not have 100% humidity. The wet bulb will always be less than the dry bulb, and that is because evaporation is a cooling process. All right, if we think about it, when we sweat, evaporation right here, when we sweat, the water evaporates off our body and cools our body. That is a mechanism that we have over generations adapted to have to cool our body down, part of homeostasis in a sense. So on page 12, we notice that we have dew point and relative humidity graphs. Okay, I will create another video or post another video on how to use these. Okay, so I'm not going to spend a whole bunch of time right now. We'll do a few practice ones. But please watch the Hammocks video on how to complete them. He does a great job and he has a lot of nice practice problems. We're covering the wet bulb and the sling psychrometer here. As we talked about, the wet bulb has a sock or a cloth attached to it, and that is to measure evaporation. We call the depression the difference between the wet bulb and the dry bulb. Okay, so if we notice in the top here of our graphs, it says difference between wet bulb and dry bulb temperatures. That is what we call the depression. It is the same thing as the difference. It's just the terminology they like to use. As we mentioned really quick, we use sling psychrometer for about 30 seconds. We swing it around, and then we would measure the differences between the two, or determine the two temperatures, and then calculate the difference. So the dry bulb, as I mentioned, is always going to be warmer than the wet bulb. In this case, the dry bulb is 24 degrees Celsius. The wet bulb is 20 degrees Celsius. That gives me a difference of 4. So here is my difference of 4. We always use the dry bulb and the difference. The dry bulb temperature in this case is 24. Remember, it's always the higher one. There's the dry bulb. We're going to use that, and we're going to use the difference to find the relative humidity and the dew point. Now, they're two different charts. Make sure you use the correct chart. I have highlighted here, we said the difference is 4 in both cases. The dry bulb temperature is 24, and what you do is you're going to find where they match. Follow dry bulb over and relative humidity or the difference down, which means that the relative humidity is 69%. The dew point temperature is 18 degrees Celsius. What that means, currently the air is 24 degrees. What it means is, if the air temperature were to drop to 18 degrees, we would have 100% humidity. We would reach the dew point and condensation would occur. Rain, dew, humidity would increase. Again, if the dew point temperature is the same as the air temperature, we have 100% humidity and chance of rain is very high. Now, here are your practice problems. I'm going to save this for a different slide, and this is kind of the one thing that you guys want to be doing on Tuesday, going over some of these practice problems. I do understand it's going to take a little bit. This one portion of the reference table does take a couple attempts and a couple practices, so please reach out if we're still confused. Please watch the Hammocks video that I've posted on the YouTube channel in the classroom, and please check your answers. All right, I'm signing off for right now. Email me, guys, and do not forget your weather project.